Hello, today thanks to Banggood I will show you a review of this Aneng AN870 multimeter, which is also sometimes branded as the ZOTEK ZT219 and also the RICHMETERS RM219. It comes in this protective pouch. Inside we have a user manual. I will leaf through it in a bit so you can see the details. Multifunctional set of probes which have threaded ends here, and you can thread alligator clips, more probes, and also some other accessories at the ends. They're not particularly high quality, but they can be useful in a lot of situations. I'll put them to the side. There is a thermocouple which has this type of stainless steel rod instead of the typical just one blob at the end of the wire thermocouple style, and the normal probes of the multimeter, which, let's see, they are about a meter long. We have protective sleeves at the end of the tips. Supposedly, actually no cat rating. On the protective sleeve it says cat 3 1000 volts or cat 4 600 volts, which is hard to determine. And the multimeter itself. I will give you a leaf through the user manual now, and then we'll move on to the review. While leafing through the user manual, I will not stop. You can pause and read if you're interested. Rather comprehensive, lots of details. Seems to describe all the functions. Here are the specs. By the way, pretty high specs on this one. We have to see when we compare it to the high performance 6.5 digit one how well it actually does. So now that we've gone through the user manual, let's take a look at the meter. First, we need to put some batteries inside. To do that, underneath the stand, takes one screw out. It is with a metal insert. There is a battery holder and two steel contacts, I presume soldered onto the PCB. There are markings, I don't know if you can see them in the video, plus minus. This is pretty tight. I think it will be reliable enough, or at least should be. values and ranges in this meter. First position off, of course. Position number 1, measuring AC voltages and frequency. What do the buttons do? The range button, by default every range is in auto mode. This is a true RMS meter, so we know the AC mode, it will measure through RMS voltages and currents. In the AC voltage mode, by default auto, with the range button we can change the range by hand. This is a 19,999 counts or 20,000 counts meter. You can see here that there is a 2, which means right now it's in the 2 volts range. With the range button I can override the auto. Here 2, 20 and 200 volts and 2000 volts and back to 2. In order to go back to auto I need to hold the range button and it goes back to auto. There is a min-max function, which if I press max now the maximum voltage will be measured. I will show you this in a little bit. Min does the same, and to switch it off again you hold it and it goes back to auto. The relative mode will set the currently measured value as a reference and then display values relative to it. You'll see this in a bit as well. In this mode I can switch to measuring frequency, which is only in auto mode. The range button doesn't do anything. And percentage duty cycle. And one more press gives me back AC mode. There is a backlight which is turned on by holding this button. The backlight has a hotspot here. I guess this is where the LED which turns it on is located. To shut it off, you hold the button again. This meter has an auto power off in 15 minutes, which can be overridden. If you go to the off mode, hold down the select button and switch it on, it will beep 5 times. This is an indication that the auto power off mode is overridden and it will not switch off. It will run until it depletes the batteries. And this is active for the current cycle until we go to off again and switch it back on. Let's quickly go to the rest of the modes. DC voltage, same functions of the buttons, ranges of 2, 20, 200 and 2000 volts. Back to auto. Again, the voltage is measured between the COM and the voltage terminal. Millivolts ranges 20 millivolts, 200 millivolts, and that's it. Ohms. On this range here, when there are extra icons above, with the select button you can change it. So we are measuring millivolts by default, but we can also measure AC millivolts because they are on the same range, and again true RMS indication showed up. Again we have 20 and 200 millivolt ranges on this. And temperature measurement. We can plug in the thermocouple and see what kind of reading we see in this room. 22 is about right. If I hold it, it will start rising. We can do a test against a reference lab thermometer later on. A third press switches over 2 degrees Fahrenheit and then back to millivolts. Next range, ohms. Auto ranging by default, and again the ranges are 200 mega ohms, 200 ohms, 2 kilo ohms, the ohm indication is up there, 20 kilo ohms, 200 kilo ohms, 2 mega ohms, 20 mega ohms, 200 mega ohms. As you see, all the ranges are based on 2, because this being a 19,999, essentially 20,000 count meter, it can display a 1 in the most significant digit, and then all 9s, which essentially makes it 20 something range. In the same position, we can measure continuity, and this is a test we're doing now. Here is the continuity. There is a very slight delay, but I suspect, no, when I make a good contact, it works instantaneously. The other option here, measuring diodes, we'll try this in a bit as well, and capacitors. On capacitors the ranges are 20 nanofarads, and there is no, the default range is 20 nanofarads, and there is no manual ranging. It will always auto range in capacitor mode. Next position, measuring frequency. It is duplicated as in the AC voltage position, but for some reason they made a dedicated one as well. Again, no manual ranging, it measures something, 22 Hz. And also with this button we can switch to measuring duty cycle. Next mode, measuring current. Both AC and DC currents are at the same position, the same 3 positions here. To switch between AC and DC, as before, by default it is on DC current. With the select button we switch to true RMS AC current measuring. Ranges 2 amps and 20 amps on this position of the dial. In DC current, same 2 and 20 amps. Current, of course, will be measured in this range on the 20 amp plug. Next position, milliamps. Again, DC and AC. Ranges 20 milliamps and 200 milliamps. Both on AC and DC. Here is on AC 20 and 200 milliamps. And the last range, microamps, again measured on here. The microamp mode will also be AC and DC, same ranges, 200 microamps and 2000 microamps, which is 2 milliamps. This mode can be very useful when measuring, for example, low power battery powered processors, embedded boards, which when they go to sleep measure a very low they draw a very low current. So this can be used to measure the sleep mode current of these boards. If I switch it back to auto range, you will see that it detects some current, because just based on noise it will detect some values. And the last position is non-contact voltage. This will detect wires wirelessly. There is a sensor up here through which there is a AC voltage. We will try this in a bit. So this is the basic set of functions for the multimeter. Now let's move on to disassembling it and taking a look what's inside. So let's disassemble it. The sleeve comes off pretty easily. The stand is on the rubber foot. Battery battery compartment comes out. These are self-tapping screws, not metal threaded with inserts as the battery compartment one. And it's open pretty easy. There is a lip on the bottom housing which goes inside a groove on the top housing. This is important for part of the safety ratings. Potted chip on board, 2 big fuses. Not as big as, for example, a Fluke Busman monsters. This is the 20 amp 200 volt rated fuse, and this is 200 milliamp 250 volt on the board marking. And the fuse itself, 200 milliamps, 250 volts. So much is the marking on the board. Not much else there. A filtering capacitor and the power supply, I presume. Here is the shunt for the 20 amp range. I'll give you a close-up of all this in a bit. Actually, I'll give you a close-up now. There is no point looking at the board at such a distance. So here it is up close, starting from the bottom. The 10 milliamp shunt for the current measurement, marked R33. Interesting thing on this board, all components have their values marked on the board. The common connector, the milliamp and microamp range one, and the 20 amp range ones. These traces are covered with solder. The 20 amp 250 volt fuse for the 20 amp current range, and a 200 milliamps 250 volt fuse for the 200 milliamp range. Diode. No, Zener most probably. The 2 battery contacts. And let's take a look at these parts slowly. As you see, all components marked with their values directly on the board. The buzzer, quartz, 4 megahertz, some unpopulated jumper, IC3 is the processor, big filtering cap here, and pretty much nothing else on the board. All these traces, I presume, go to the display on the other side. The board is held by 3 screws, and I'm not going to take it out. I don't think it's necessary, but as far as protection, an NTC here, and nothing else that I can see. This seems to be the voltage reference, ICL 8069, and another IC here, most probably an EEPROM, yes, with some calibration coefficients for the processor. Let's put it back together and see. So now that we put it back together and hopefully didn't break anything, let's try to measure something, see if it still works. Most trivial measurement possible. I'll measure this 18650 lithium-ion battery. Get a reading 3.6661 volts. Pretty nice. The measurement settles fairly quickly, and then the last digit changes in about 5 seconds. Interesting. And I have here a pile of bad capacitors taken out of an old motherboard. Go to capacitance measurement. They are electrolytic, so you should watch the polarity when measuring them and see what these guys will show in the different modes. I mean what the different ones will show as measurement. As you see, it takes a while. 2 millifarads. Look at the range here. This is essentially 2000 microfarads, and this capacitor is rated at 1800 microfarads. This sounds right. And some of them should be bad. What I'm doing here is not particularly good, but I'm not touching both pins with my fingers, so I should not be affecting the capacitor. See, this is 1518 microfarads, again millifarad range, which is not very typical. You should watch for this. So this is way off, and you can see that it's actually leaked. This one is bulged quite a bit. Let's take a look. I stopped touching the pin for a bit. 3000 microfarads when it's actually rated at 1800. We'll compare this to a reference meter later. Now, interesting point. When the meters are measuring diodes and measuring continuity, there is an important factor. How much voltage are they using to measure continuity and diodes? When measuring continuity, they should be using the lowest possible voltage. Today I will also compare this meter to another one from the same company, Aneng AN8009. Comes with pretty much the same accessories, except that the probes are a bit shorter and smaller. I think you can see them. This is not interesting. What I'll do is I'll put this in voltage range, and I've configured the multifunction probes to be banana plugs on both ends. This will allow me to measure voltage with this one and the small guy. And if I switch to ohm measurement, we can see that this meter, while measuring ohms, is using only 500 millivolts to measure it. And on the other side, we can see that the input resistance of this meter is 11 mega ohms. If I switch to continuity tester, you'll see that the AN870 is using 1 volt pretty much, 995 millivolts to measure continuity. This is good. It uses a fairly low value. And in diode mode, it is using 3.25, 3.3 volts, which is good. This means that it will be able to measure a lot of LEDs, but some of the higher power white ones will not be able to turn on, because there are white LEDs that turn on around 4.5–5 volts and even more. We can reverse the exercise just as a comparison. I can put this in voltage measurement mode and this in resistance measurement mode. So now this is measuring again 11 megohms, which means the input resistance of this multimeter when measuring voltage is 11 megohms. At the same time, the small one, when it's measuring resistance, is using 500 odd millivolts, which is nice. Now I can switch the mode on this one to measuring ohms, 1 volt, measuring diodes, 3.3 volts, just like the big one, and that's it. So, bottom line, continuity, we didn't test this one. When it's measuring continuity, 1 volt. So they're pretty much the same in this respect. They're using 1 volt for continuity measurement and 3.3 volts for diodes. This is nice because it will allow us to measure some diodes. And their input resistance on the voltage range is 11 megohm for both. Here again, 11 megohm. We can try the AC voltage input resistance, 11 megohm. The millivolt range input resistance, too high to measure for this guy. We can reverse the exercise. The millivolt range for this meter measured by this meter, again out of range. So it means that in the millivolt range both of them have very high input resistance, which makes sense. There is another meter which I want to use for comparison today, and a little bit later when we are measuring doing the detailed measurements. This is the Mustool MT826. It's a big meter. By the way, this little guy is 10,000 counts, 9,999. This big guy is also true RMS. By the way, the small one is also true RMS. The advantage of this one is that it has actually a computer interface with an optically isolated USB port. This meter I will use as another comparison point when measuring the performance a little bit later. So this is the set of meters you will see. I will compare the voltage and current measurements as well as resistance. We will try some frequencies and duty cycles if we get our hands on a function generator, and we may try to compare or test the true RMS performance of them. So let's move over to a better equipped lab to make these precise measurements. Well, welcome to the lab. Let me present you the contestants. First, the power supply. It's a Aneng AN870. 1 kilowatt power supply can give up to 50 volts or 50 amps or a combination thereof. The star of this review, the Aneng AN870, the Aneng AN8009, its little brother, the Mustool MT826, and in the back, the big guns, the 6.5 digit multimeter, a Hewlett-Packard 34401A, and the function generator, the Agilent 32220A. So, let's start with measuring some really small voltages, DC. 10 millivolt on the power supply. The blue wires are coming from the power supply. Everything else is a mess, but essentially all the multimeters are connected together. The function generator is not connected right now. I'll use it later. So this multimeter, apart from being a 6.5 digit reference one, is calibrated semi-annually. Last time in September 2018. So it shows 9.16 something volts. These guys right now are not in their right range. This is volts, so let's switch them to millivolts. Anyway, it shows a pretty decent value. Millivolts on this one, millivolts on this one, and this guy is already on millivolts. So you can see the two Anengs agree with the reference one to within, I would say, 10 microvolts. As you see, the power supply varies a little bit, and the Mustool is off by 30 microvolts. This is a very low voltage for this supply, so let's go up a bit. By the way, this also has a current limit, which now is limited at 100 milliamps. So 20 millivolts, 30 millivolts. You can also see the settling time for everyone. You can pause the video as you watch if you want to see the particular readings. 40, 50, 60, 70, 80, 90, 100 millivolts. Well, when was the voltage is a bit up, everybody is pretty much within range. As you see, there is something like a 10 microvolts difference between the reference one and the Anengs. And this guy, since it's only, I believe, 4,000 or 6,000 counts, is already switched to the next range. So let's go in 100 millivolt steps now. 100, 200, 300. These two are out of range now, so I'll switch them back to the voltage range. Since you saw in the beginning of the review, their millivolts highest range was 200 millivolts. Interesting experiment. Let's try this. I will see how many digits maximum they can display. So they can display, and this is set to 199.30, this sample shows 199.33. This is already showing over. However, let's try to change in 10 millivolt steps down. So the small Aneng AN8009 is completely logical. It's a 10,000 count multimeter. It will go over at 9,009, basically 100 millivolts. So I need to switch it to the higher range, while this guy will continue up to 200 millivolts, and I can try a bit more. No. So this is the highest range in millivolts for this one. Now we'll need to switch him to volt. So 200 millivolts, 300 millivolts. As you can see, they're pretty much up to the Last significant visible digit in complete agreement. Well, this is 1 microvolt off. So let's go up. I'm not going to comment on this anymore. You can just make your judgment by pausing the video and looking at the values. 400, 500, 6, 7, 8, 900 millivolts. Now this went out of range, so I'll switch it to voltage DC. One volt. Pretty nice. 5 volts. Let's see. At 5 volts, basically no difference between the AN870 and the Hewlett-Packard. Practically 20 millivolts on the small one, and 2 millivolts on the small one and 3 millivolts on the Mustool. 10. Pretty nice. You heard the Hewlett-Packard auto switch to a higher range. Here is 15. I'll let you judge. 20. And I'll go in 10 volt steps from now on. 30. 29.99, 30 with 3 millivolts on top. 29.95. This is still a bit off. 40. This is playing a little bit, and 50 is the highest voltage that this power supply can show. No, 40, I'm sorry, is the highest voltage that this power supply can give. So, let's switch over to AC. For the AC, I'll use the function generator. This is its output. I'll stop the video in order to reconfigure things. Here is AC voltage. The function generator is set at a sine wave, 1 kilohertz, 100 millivolts peak to peak, offset of 0. This is set in voltage AC, 70.46, whatever. 70. This is interesting. In its millivolt range, it cannot really measure this. If I switch it to voltage, yes, I was not in AC mode on this one. 70.6, 70.58, 17.55. Measuring a sine wave should not be a problem, since average and RMS are the same. It would be interesting if we start increasing the frequency in 1 kilohertz. Step 2, 3, 4, 5, 6. Let's do up. The small ones fell off. Watch the displays. So up to 1 kilohertz at such a small voltage, this is only 70 millivolt, they're measuring fine. However, at 2 kilohertz their readings are already starting to drop off. 3 becomes, and 4 kilohertz is completely out of their field. Let's keep it at 1 kilohertz, try a square wave. They're RMS multimeters, so they should all be able to handle it. And you see 93, 93, 93, 99 on the reference instrument. Triangular ramp. I'll let you watch the numbers and make your own judgment. This can even generate noise, but it's a rather crazy thing, so it will be a little bit weird to do this. So this is a noise with 100 millivolt peak to peak. However, this is a meaningful thing only for an oscilloscope, so I'll not use this mode. Let's go back to sine and raise the amplitude. We will make it 1 volt peak to peak. Sine wave. These guys are out of range, of course. Well, no, let's do something else. We will give them a chance in their 200 millivolt range for this one. So at 200 millivolts, 141, 141 practically. This is out of range, of course. And it does, oops, sorry, I should be in AC mode on this one. 141, 141. Pretty nice. Let's try to raise the frequency. 2 kilohertz. 3 kilohertz, the cheap multimeters. Now, none of these is more pricier than $50, while these are both thousands. So it's a little bit of an unfair comparison, but as you see, at 3 kilohertz, these are starting to drop off significantly, but not as bad as when we had 100 millivolts. So let's go to 1 volt. I'll switch this guy to AC voltage. I'll switch this guy to, it's already at AC voltage, sorry. Let's see, half a volt. Millivolts, 353 millivolts. This has a useful range here, which this guy is lacking, as you see, because it, no, sorry, I should be in AC voltage, of course. So 354 millivolts, 352 millivolts, 353 millivolts, 354 millivolts, very close. Square wave. And triangular ramp. All of these at 1 kilohertz. Raising the frequency, 2 kilohertz, 3 kilohertz, and again, these are starting to drop off badly. So, raise the level up. Let's make it 5 volts peak to peak. Now this is out of range. It should be in AC. As you see on these two multimeters, the voltage is shared even in the voltage range between DC and AC, while this one has a separate setting for AC and DC voltage. Anyway, pretty much in agreement. Square wave. And triangular wave. This time I'll try raising the frequency starting with the triangular wave. 2 kilohertz, square wave, sine wave, 3 kilohertz, 4 kilohertz. And you can see that none of them are able to really measure at these frequencies. We'll make the voltage a bit higher again. 10 volts is the highest that this function generator will go to. 7 volts RMS and sine wave. Here is square. Triangular. So as you see, they are all real true RMS meters. However, they don't handle higher frequency as well. The reason is that their sampling rate internally is probably much lower than the HP meter. This generator can go to boringly high frequencies, which are not interesting, but it would be interesting to watch the HP meter for once. So let's start with 20, 30, 40, 100 kilohertz. Two, 3, 200 kilohertz. Oh, I'm sorry. This is set to European standard. This is 200 megahertz. So all of the measurements I've been doing up to now, you should take with a grain of salt. So when I was doing this, let me take a look at this. No, it's kilohertz, of course. So, sorry for that. So, 10 kilohertz, 100 kilohertz, and 200 kilohertz is the highest this will go. As you see, the HP doesn't bat an eye. The value barely changes, while these guys have a bit of trouble above 1 kilohertz. So this is for frequency measurements. I think now we should try some resistance, and then we'll see. Perhaps no, let's do something else. Let's see how precise these guys are measuring frequency. So I'll switch this to frequency. I'll switch this to frequency here. I'll switch this to frequency. And I'll switch this to frequency. Okay, beautiful. 1 kilohertz across the board, very precise. And this guy has an opinion. 2 kilohertz, 3, 4, 5, 6, 7, 8, 10 kilohertz, 20, 30, 40, 50, 100 kilohertz, 200 kilohertz. This one is having trouble. Well, the small Aneng and the Mustool are perfect. Let's figure out at what point this one starts to have trouble. So at 130 kilohertz, they're all fine. Yeah, at 135 kilohertz, this peaks and will not go any higher, or at least starts to be very non-linear. Which is interesting. I don't know why this was limited in such a way. The others comfortably go to 200 and are in pretty much perfect agreement with the high-end meter. And this is thinking that we actually have 100 kilohertz here. So there is something, probably a firmware problem with this one, which limits its ability to measure above 135 kilohertz or so. By the way, we are at triangular wave. Let's see what will happen with square. This one fixed itself. So the triangular wave gives it some trouble. So this is highly likely that this is a firmware bug in here, because when I switch to square wave, it has absolutely no problem with 200 kilohertz. By the way, see how long this takes to settle. And now sine wave. This is still thinking, and 200, 200, 200. Very good. So this probably has some small firmware issues with triangular waves, but this is not really the intended purpose of these meters. This can also measure duty cycle, as can this one. 50% duty cycle, 48.3% duty cycle, and this 49.9% duty cycle at 100 kilohertz. I'm not sure if this can measure duty cycle, but I don't care. 100 kilohertz, and at the lower frequencies they should absolutely have no problem to show a perfect 50% duty cycle. Let's try the square wave. Perfect 50%. You can watch the readings. Pretty much perfect. Triangular. Oh, it's an interesting thing what a duty cycle means for a triangular wave. So let's see their opinion. 51%. Since this has no offset, it makes sense this to be a 50% duty cycle, but it's a little bit strange. So let's go down. So these two think that there is a 50% duty cycle on this symmetrical triangular wave, 100% symmetry. But this guy again has some doubt. Let's lower the frequency and see what happens. Now this also thinks that it's 50% duty cycle. And if we go lower, 50 kilohertz, 10 kilohertz, 1 kilohertz, they start to agree more or less. But this is now torture. The next test, measuring some resistances. I'll not do much, but I'll try a few. I'll stop the video to reconfigure. So, all the wires are gone. It's a nice bundle. And I have a 6.8 ohm, 1%, 50 watt resistor with some very short wires on it. Let's see. And I'll plug it directly into each multimeter. Thinking, 10.9 ohms. Okay. This is not going to measure any voltage, of course. 14.5 ohms. Interesting. I wonder whether I should allow them to calibrate. No. $17 ohms. $11 ohms. $7 ohms. 9 ohms. I don't know what's going on with this one. Every time I plug it in, it shows me a different value. Nothing. I wonder whether these guys calibrate upon entering the resistance mode. Yes, most probably. 11 ohms. I'll power cycle this and go to ohms as well. So 11 ohms. 9.6 ohms. 11.8. Okay. Fair enough. 12.4, 12.4, 13, 8.4. It's interesting. And these are pretty decent banana plugs. Shouldn't show such a big difference from time to time. 13 ohms, 15 ohms, 14 ohms. Let's see what this one has to say. Of course, I want to measure ohms. 7.4 something. Seven 7.9, 7.8, 7.8, 8.2, 9, 9. Just touching and shaking the resistor shows differences, so I wonder if I have a bad connection in one of these banana jacks, but I doubt it. Anyway, $7.1. $8. You should take all this with a grain of salt. 7.8. Okay, perhaps since this has not been used in a very long time, the banana plugs were oxidized and giving significantly different readings on this resistor. I'm not going to do any more resistance readings. I'll try some capacitors now. So I have a 470 microfarad SMD capacitor down here connected to these wires, and I'll just plug the other ends in each multimeter one by one. They're all set to capacitance mode. $460 microfarads after some thinking. $460 microfarads, much faster than the Mustool. $460. See, 462 and dropping. This is drifting. But let's say 462 microfarads. They're pretty much in agreement with this one being the fastest to measure. You can see. And done. By the way, when measuring capacitors, if they're very high voltage, high capacity ones, you can always damage your multimeter if you plug it in directly. So you should discharge them before plugging them in. The HP cannot measure capacitance, so I'm not going to do that. Here is one more time to see repeatability. .462, 459.8. Different reading, but pretty much 460. And again, the capacitor is 470 microfarads nominal. .461, very fast. Let's see, it drifted to 159, to 459. .459, yeah. To be fair to all of them, I should be discharging the capacitor each time, but I'm not particularly concerned about the speed of measurement. This one always starts from a higher value and slowly drifts down. So, this is it. Let's measure some current. Sorry that you just had a glare on the screen of this one when measuring capacitors. So, the amazing thing about this power supply, not so amazing, but is we can current limit it. Right now it's limited to 10 milliamps, set to 5 volts. When I switch the output on, what I've done is from the power supply, through the HP, through the Mustool, through the big Aneng, through the small Aneng, and as you can see, the power supply cannot of course control small currents as precisely, but they are all measuring pretty much 16 milliamps. This has a 3 amp maximum current, and the fuses on all of these on the milliamp range on these two are 200 milliamps, and this is 600 milliamps. But what I'll do is I'll keep the milliamp range measurements up to 100 milliamps to make sure I don't scrub the fuses. No comments, just I'll go up with the power supply. This is 50 milliamps according to the power supply. 70. 100 milliamps. You can see that it's in constant current mode, and it's limiting the voltage even though we have set it to 5 volts. You can see how close all the multimeters are to each other. I will try to go to 150. It shouldn't cause any trouble to any of the multimeters. Here is 150 milliamp of current. All of them pretty much perfect. The small Aneng is a bit off, but this is truly insignificant. I'll switch to the amp mode now. To do this, I'll simply plug the jacks into the higher range on these guys. This doesn't have a separate range, and I'll switch this to amps, switch this to amps, and this is already, as I said, on amps. We don't need to do anything on the HP. Turn the output on. 150 as we started. 200. And I'll go up to 5 amps. I don't want to. I will increase the voltage now since the burden is becoming high. These guys. .300 milliamps, 400, 5, 1 amp. Current. I should not go above 3 because this will not hold it. I'll go up to 2.5. 2, 2.1, 2.2, 2.3, 2.4, 2.5 amps. In my opinion, they're all performing pretty much perfectly. Let's measure some AC current. To do this, I've connected our resistor through the HP, through the other multimeters, and down here back into the function generator, sine wave. Let's start with 100 millivolts peak to peak. They're all in their microamp range. The HP cannot measure less than 10 milliamps. So it will show us some number until we go to higher ranges. So this should be in AC mode, and this should be in AC mode. As you see, 194 microamps for all of them. Perfect. If I switch to a square wave, 256 microamps. Triangular, 142. I'll go to 200 millivolts. By the way, the frequency is 1 kilohertz. We can try higher frequencies. 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz. As you remember from the voltage test, they don't do so well at higher frequencies. Let's do a higher voltage. 400 millivolts. This is now overloading on its microamp range, so I should switch over to milliamps. And should do AC. It will, of course, not be able to show me anything because we are at still microamps. You can see how much the current raised on these two, because this obviously has a So next test, I'll switch to the milliamp range on these guys. And we can start seeing what's happening here. Four microamps. This is a square wave, by the way. Let's do a sine. 3, 5, 5, 4. A bit higher voltage. This should be in AC. This should be in AC. I'm not measuring anything, of course. Yeah, now it's good. 6 milliamps, 6 milliamps, 6 milliamps, 6 milliamps. Beautiful. I'll lower the voltage to see the values again. And you can follow with me. At 4 milliamps, let's try square. And triangular. And square and sine wave, these are doing pretty well. In triangular, they start disagreeing with the HP, which of course is a true RMS. I'll go to sine. I'll raise the voltage half a volt. Let's go to some higher current. 16 milliamps across the board. Square wave. Triangular wave. They're pretty close. This is pretty good. I'll try raising the frequency now, starting with sine. 1 kilohertz, 2 kilohertz, 3 kilohertz. As before, the 3 kilohertz, these guys start to seriously drop off. Up to 2 kilohertz, they're fine. On square, do they do any better? 2 kilohertz is fine. 3 kilohertz, they start to drop off significantly. Same as before. And triangular, 1 kilohertz, 2 kilohertz. They are already in significant disagreement with DHP, and now they are completely off. A bit higher current again. I'll adjust this at square wave in order not to overload anything. $70 milliamps. I'll try to go to 100. 88. 103 or so milliamps on a square wave with 7 volt peak to peak through the 6.8 ohm resistor. Everything pretty much agrees. Here is the sine wave. Perfect agreement. Triangular wave. Again, these always show a smaller value than the HP when measuring the triangular waves. And let's try to go up in frequency. 2 kilohertz. And again at 3 kilohertz, these guys start to drop off and completely lose their mind at 4. Is square any better? 1, 2 kilohertz. 3 kilohertz, significant drop-off. Same as always. We are not expecting any difference anyway, because this is only based on their sampling frequency inside. Let's try a bit higher current again. And I cannot do it because this has a current limiter of 100 milliamp inside, and it will not allow me to do so. So this will be all for current measurements. I think they're both doing pretty well compared to this very high-end reference instrument. And even in the low ranges, they're pretty close. Again, these should go to their microamp mode to have a fair comparison in this situation. On the small one, of course, it's inconvenient that you have to switch over here and go to microamp and AC in order to measure anything. But as you can see, they're all pretty close. So, after all the big instruments are gone through the magic of editing, let's measure some diodes, as I promised you earlier. .56 volts. Nothing in reverse. Let's try some of these. 2.48 volts. And of course, nothing in reverse. On this board, nothing. Oh. 2.55 volts. You can see the others lighting up as well. And nothing in reverse. It works. So, I hope you like this review of the Aneng AN870 provided by Banggood. If you did like it, give it a thumbs up. I have left a link in the description to all 3 multimeters in case you want to purchase them. Thanks for watching and have a good day.